introduce Dr. Kyra St, who is an aquatic biogeochemist with an interest in understanding the cycles of carbon, nutrients, and contaminants across and between terrestrial, freshwater, and marine ecosystems. Dr. St. began her research career using isotope-enriched tracers of mercury to quantify rates of mercury methylation and demethylation in coastal sediments of the Canadian Arctic archipelago under different environmental conditions. Her PhD thesis at the University of Alberta examined the impacts of enhanced glacial melt on the biogeochemical cycles of inorganic carbon, mercury, and nutrients in the Canadian high Arctic, from glacial headwaters through a large lake into the nearshore environment. More recently, she has been involved in several projects aimed at better understanding the mercury cycle across Arctic ecosystems, from small-scale physical and microbial transformations to the bioaccumulation of mercury in polar bear tissues. Building on these experiences, Dr. St. Pierre's research with the Hakai Coastal Initiative and aims to understand how the quality and quantity of freshwater exports from the coastal temperate rainforests along BC's central coast change over time and space. Now for our panelists, first I'd like to welcome Dr. Isabelle Lorient, who is a professor of aquatic and biooptic ecology at the Institut National de la Recherche Scientifique in Quebec City. As the scientific leader of the Aquatic Biooptics and Biogeochemistry Laboratory, Dr. Lorient and her team study the effects of climate change and permafrost thawing on lake water transparency and mixing dynamics, and their multiple impacts on the microbial food chain, greenhouse gas emissions, and oxythermal habitat. And finally, I'd like to welcome Dr. David Olefelt, who is an assistant professor and Campus Alberta Innovation Program Chair in Wetland Restoration and Catchment Management. Dr. Olefelt's research group studies impacts of climate change, disturbances, and land management practices on catchment and wetland functions with a focus on northern peatlands. Research foci include greenhouse gas fluxes, water quality, soil biogeochemistry, terrestrial aquatic linkages, permafrost thaw, wildfire, thermokarst, and soil carbon storage. So you can see we have some really excellent experts in this topic of greenhouse gas emissions. So without further ado, I'd like to pass the screen over to Dr. St. Pierre. Thank you.
Great. Can you all see my screen? It's not showing here.
Yes, we can.
Okay, perfect. Awesome, thanks. So thank you so much for that introduction and for having me today. I'm really excited to be here. And so even though this is virtual, I'll first start by acknowledging that I'm speaking to you today from the traditional, ancestral, and unceded territories of the Musqueam, Squamish, and Tsleil-Waututh people in what is now known as Vancouver. So greenhouse gas dynamics in the Arctic is a large and really complex topic. So I'm really going to focus on this from the perspective of climate change. And so these four kind of classes of gases shown here are those that are formally recognized by the United States Environmental Protection Agency as being indicators of climate change. So we can see carbon dioxide, methane, nitrous oxide, and the fluorinated gases. So for simplicity's sake today, I'm going to focus primarily on carbon dioxide, but we'll also touch on some methane in a couple of examples, but just acknowledging that these aren't the only greenhouse gases and that there are others still like ozone and water vapor that aren't fully encompassed by these four categories here. So greenhouse gases by definition are those that absorb and emit radiant energy within a certain range of wavelengths and therefore contribute to the warmth that we feel and make the planet habitable. These gases are fundamental to the function of the Earth system, and most of them occur naturally in the environment in some concentration. But in recent times, human activities have contributed to massive increases in concentrations within the atmosphere. And that's what you can see in these panels here at right, where we can see concentrations of carbon dioxide at top, methane in the middle, and nitrous oxide at bottom. And in the left panel, this is showing over geological timescales. And on the right panel, we can see these increases over kind of more relevant human timescales. And so these increases have resulted in an increase in the capacity of the atmosphere to retain heat, which has fundamentally altered the energy balance of the planet. But these changes are disproportionately affecting the Arctic. So this figure is from the Intergovernmental Panel on Climate Change report, showing rather conservative scenarios for winter temperatures at left and terrestrial runoff on the right under climate change scenarios. So we're actually in the middle of what this predicted period is. And one consistent feature of these figures, whether it's showing realized or predicted changes, is that the most dramatic changes are happening in the north. So when I was thinking about how to frame this topic, I initially thought, well, the mechanics of greenhouse gas production and consumption in Arctic freshwater ecosystems is essentially identical to what we see in more temperate systems. But there are a handful of characteristics which taken together really distinguish Arctic freshwaters and influence greenhouse gas dynamics. So I've divided those here as kind of primary characteristics at top and the derivative characteristics, which are the three smaller pictures at bottom. So Arctic freshwater ecosystems are ice covered for some or all of the year. As you can see, the zooplankton net here through 2 meters of lake ice. And the watersheds are underlain by permafrost, as evidenced here by this polygonal ground in northern Nunavut. But because of the ice cover and cycles of 24 hours daylight and 24 hours night, there is reduced light and or long-lived ice covers will also limit atmospheric exchange for some or all of the year. But because of the permafrost and shortened growing seasons, there's lower terrestrial productivity within the watershed, which does affect freshwater ecosystems. And we can see these seasonal fluctuations in light and energy availability result in very distinct thaw and melt seasons, shown here by this glacier between the spring and kind of summer seasons. So all of these characteristics are highly sensitive to temperature and precipitation. So when we overlay climate change on top of these basic characteristics, we're able to actually see dramatic manifestations of climate change within Arctic landscapes that have direct consequences for greenhouse gas dynamics within freshwater ecosystems. So we can see climate change manifested as permafrost slumps along the edges of rivers, lakes, and coastlines. And these slumps are capable of mobilizing large volumes of materials to adjacent downstream freshwater ecosystems. And just a plug for the next LIMNO seminar, I think this will be the topic that Dr. Emily Stewart is talking about. So we can see climate change manifested as net glacier mass loss in some Arctic ecosystems. And we can see climate change manifested as pond, lake, and wetland expansion or loss, as demonstrated so poignantly here in this 2018 paper led by Alex Matveyev. So if we take these changes all together, it becomes apparent that climate change is fundamentally altering the connections between terrestrial and freshwater ecosystems. Land is becoming water in some cases, and water is becoming land in others. We're seeing increasing runoff and discharge as a result of increases in precipitation combined with changing melt or thaw regimes. More materials are being mobilized from landscape destabilization through permafrost thaw, but also increasing erosion along river and stream corridors that are occurring with this heightened runoff. And then finally, we're seeing an emergence or maybe even explosion of wildfires in Arctic environments that are capable of transporting kind of terrestrial materials over both short and long distances. So then the question becomes, how are these changes affecting greenhouse gas dynamics? And so I'm showing here carbon dioxide at left and methane at right as examples. And within freshwater ecosystems, we have this constant push and pull between multiple biological and geochemical processes that govern the production and consumption of greenhouse gases. So in each case, I'm showing arrows showing the change that a certain process will have on the gas concentration. So for example, if we look at photosynthesis, the arrows indicating that you see a consumption of carbon dioxide through photosynthesis. So if that were the dominant process, we would see a reduction in the concentration of carbon dioxide in the water. But the net sum of these processes really determine the relationship that the water body has with the atmosphere. And so whether it's a source or sink of greenhouse gases to the atmosphere. So if the concentration of, say, carbon dioxide in the air is greater than in the water, we would see a net flux of carbon dioxide from the air to the water, and the water is said to be a sink. If the concentrations are equal between air and water, the system is said to be at equilibrium. And if the concentration of carbon dioxide in the water exceeds that in the air, we would see a diffusion of that greenhouse gas to the overlying atmosphere. And the water is said to be a source of the greenhouse gas to the atmosphere. And the same would go for methane in this particular example. Now, this would all be fine and straightforward if freshwater ecosystems were self-contained jars. But the reality is that the surrounding watershed contributes a vast amount of material to freshwater ecosystems that act to subsidize, inhibit, promote, or diminish these various processes to differing degrees. And it's really the identity of these materials that determine what effect they'll have on the ecosystems. So materials rich in organic matter tend to promote biological processes and specifically respiration, which tends to increase concentrations of carbon dioxide to the atmosphere. And this tends to be a dominant pathway for many freshwater ecosystems. And it's the reason that we have the paradigm of kind of these freshwater ecosystems as almost universal sources of carbon dioxide to the atmosphere. And this is especially true in kind of smaller systems in the Arctic, especially in the more southerly sub and low Arctic regions, where soils are better developed and terrestrial productivity is higher than what we see in the most northerly areas. So these are just a subset of some of the papers that have come out in recent years kind of documenting this effect, and they come from all over the Arctic. So we can see greenhouse gas emissions from diverse Arctic Alaskan lakes are dominated by young carbon, high methane emissions from thermokarst lakes and subarctic peatlands, high carbon emissions from thermokarst lakes of Western Siberia, and kind of the impacts of heat waves on greenhouse gas production in thaw lakes in the discontinuous permafrost zones. And so in this really nice study that was led by Kenzie Kuhn, we can see that this landscape evolution, and in this case, we're talking about a case where land is becoming water, as you can see in this figure at left, where we see this kind of trajectory where we're starting with one maybe thaw pond within kind of this wetland complex. And those number of thaw ponds are increasing as permafrost thaw kind of proceeds. But the impacts of this change on the landscape has really non-trivial impacts for our understanding of the carbon budgets and greenhouse gas dynamics of these hot Arctic landscapes. And so this figure at right is showing carbon exchange as the sum of net carbon dioxide and methane fluxes. And so if we only account for the terrestrial systems, which has often been done in many of these landscapes, we'd see the landscape as a large net carbon sink. However, because of permafrost thaw, these thaw ponds are actually overwhelming emitters of carbon dioxide, which actually serves to diminish the terrestrial carbon sink. And so we would expect kind of under future scenarios that expansion of these ponds could lead to a further reduction in the carbon sink of these landscapes. And in cases where we're seeing the drying up of these ponds, we would definitely expect the reverse to be true as well. So we've seen the impact of organic matter inputs, but there's also substantial quantities of inorganic materials being mobilized to downstream aquatic ecosystems from watershed changes like permafrost lumps, as well as enhanced erosion by rivers and streams. And the input of inorganic materials tends to favor geochemical processes over biological ones. And in some Arctic environments, these chemical weathering processes in particular can really dominate the dynamics of carbon dioxide within freshwater ecosystems. And so chemical weathering reactions are really ubiquitous in aquatic ecosystems, but the extent to which they influence carbon dioxide dynamics really depends on the landscapes that surrounds them. So without getting into the chemistry too much, these reactions typically involve a mineral and an acid or dissolved gas and water. And then what happens next depends on the mineral, but also the nature of that gas or acid. So I'm showing a couple of examples here. And you can see that even though kind of the starting products are quite similar in nature, the end result is quite different in terms of carbon dioxide. So we can see an increase in carbon dioxide here and decreases in carbon dioxide in these latter two examples. And so I'm going to provide a couple of examples of systems where these tend to be the dominant processes. So Scott Zolkos and colleagues were studying the impacts of these retrogressive thaw sumps, which you can see at the top right, on greenhouse gas dynamics. And they were observing these really high concentrations of dissolved carbon dioxide within the runoff of these thaw slumps. And so that's what we can see here in this panel at left, where you can see the partial pressure of carbon dioxide, and this is on a log scale across 8 different retrogressive thaw slumps, and in relation to that atmospheric equilibrium of carbon dioxide, which you can see here by the dashed line. And so these runoff samples are in comparison to kind of these pristine samples, which are upstream or in unaffected areas of the landscape, and in relation to reaches of the streams that are much further downstream. So after there's been quite a significant off-gassing of this carbon dioxide. And so while it might have been expected that these high carbon dioxide concentrations were the result of biological processes, the geochemical signature, as evidenced by both the stable isotope signature of carbon, which I'm showing here, and the major ion profiles within the runoff, was consistent with mineral dissolution by sulfuric acid, which is a byproduct of the large shale deposits within the region. So this is where we're seeing this kind of net increase in carbon dioxide and this large flux of carbon dioxide to the atmosphere. But while the input of inorganic materials can lead to net carbon dioxide emissions, the reverse can also be true and is a function of the landscape inputs as well. And so over the next, I'm going to really focus on a couple of examples here in relation to glacial systems, which are kind of my coup de coeur, and looking both at carbon dioxide, but also touching on methane a bit. And so this was a study that we did over a couple of years within the Lake Hazen watershed on northern Ellesmere Island in Nunavut. And these results were published in 2019 in PNAS. And so this was supported by a number of government institutions, which I've acknowledged here on the right-hand side. And so our guiding research question was, how does glacial melt affect freshwater greenhouse gas dynamics? And so we used the Lake Hazen watershed in high Arctic Nunavut on Ellesmere Island as a model watershed to ask this. So this watershed is 7,500 square kilometers. It's around 40% covered by glaciers. And at the heart of the watershed is Lake Hazen, which is actually one of the world's Great Lakes at 544 square kilometers and 267 meters deep at its deepest point. And so to really kind of get a picture of what was happening across this watershed, there were several components to this sampling scheme. So we conducted transects along the length of several rivers, as well as samplings across a number of different deltas by helicopter. We did bi-weekly samplings of 2 rivers that were within hiking distance of our base camp. And we did pseudo-continuous sampling of nearshore waters along the lake edge. And pseudo-continuous because the lake ice had other ideas during some times of the year. And so we also conducted water column profiles during both the open water and under ice seasons, and that's shown here. And this is going to come up in a bit, but these profiles were done at locations that are far from the direct influence of glacial inputs. And so the final component of the watershed really is this outflow, the Ruggles River, and I'm not really going to touch on the Ruggles River today. But kind of the backdrop and the history of this watershed is that we've really begun to see a strong increase in temperature across northern Ellesmere Island. And so since the start of the 2000s, we've seen a 1 degree Celsius increase in temperature, which has really resulted in an increase in the glacial inputs to the lake. But at the same time, we're seeing conditions where the lake used to remain ice covered throughout the year, but it's now a virtual certainty every summer that the lake goes ice-free. And you can see this here in 2015 in the bottom picture. So the landscapes of the high Arctic have very little vegetation cover, and the successive cycles of glacial advance and retreat have created these large deposits of finely ground sediments. And so the further that you move away from the glacier, the more finely ground sediment there is, such that visually, the river changes quite substantially from its headwaters and boulder fields through to more easily erodible sediment deposits. And so I love this picture in the middle here where you can see Maria Cavaco, who was a master's student working on Lake Hazen, for scale, just in relation to these massive deposits of finely ground sediments through which the rivers are obviously undercutting. And so by the time the river reaches a lake or coastal waters, it looks very different from when it started. And so I'm kind of on this mission to remove the illusion that glacial meltwaters look like this, brought to you by the bottled water industry. And the reality is that glacial meltwaters actually look a lot more like chocolate milk than something that you would necessarily want to drink. So along these river lengths, we can see that the river changes quite substantially. And so the particulate load in particular is increasing along the river length. And so that's really affecting the mineral content of these rivers. And so that we see this stark visual difference at each of these sites. And so these sites were occurring over about a 27-kilometer distance. But that difference is not only visual, it's also chemical. So when we think about carbon dioxide, it's really just one component of dissolved inorganic carbon, which also includes bicarbonate and carbonate ions. And so that's that equation here at top. And so the dissolved inorganic carbon as a pool reflects the sum of terrestrial inputs, net respiration, so the generation of carbon dioxide, chemical weathering reactions, and in some cases, influx of carbon dioxide from the atmosphere. So in the absence of vegetation and soil development, terrestrial inputs to these systems are really dominated by inorganic materials. And consequently, there's very little respiration contributing to this overall balance in this system. So in the absence of the large sulfide deposits like we saw in the Western Canadian Arctic, chemical weathering within these systems is dominated by dissolution reactions instigated by dissolved carbon dioxide. And so these reactions, so I've got two of them as examples here where you can see carbonate is one mineral, and this is anorthite, which is just one example of a silicate mineral that is present within these watersheds. You can see here where you have the mineral reacting with the gas in water to produce a cation, in both cases calcium, and bicarbonate ions. And so in silicate dissolution, there's also this kind of secondary mineral that's produced because the dissolution typically isn't complete. So these are three glacial river transects, and it's important to note here that the glaciers are really the only major source of water to these regions. So the amount of water stays the same between the glacier terminus and the river delta. But because of reactions occurring around the sediments, we're seeing increasing concentrations of dissolved cations like calcium, magnesium, potassium, and sodium, but also silica, which is a much smaller increase here, which we would actually expect, and increases in dissolved inorganic carbon. And so what's interesting is when we look at the dissolved gas profiles here, so this is carbon dioxide and oxygen saturation, where 100% indicates where the waters would sit, or where the concentrations would sit if the waters were in equilibrium with the atmosphere. And so we can see oxygen here, that they're kind of universally at 100%, which is indicating that these waters are well mixed with the atmosphere. But when we look at the carbon dioxide saturation, it's actually a very different story. And so here we can see that the carbon dioxide is well below atmospheric equilibrium, indicating that there's this kind of imbalance between the atmosphere and the waters. And so when we take into account not only these kind of geochemical profiles that we're seeing here, but also stable isotopes of dissolved inorganic carbon, it's suggesting that it's likely these chemical weathering reactions that are driving these observations. And so in this particular case, we're seeing a system where the concentration within the water is much lower than the air. So we would expect the water to be a net sink of carbon dioxide from the atmosphere. So we measured carbon dioxide flux along the lake shoreline in between two glacial river inputs. And so this is contrasting 2 years where the meltwater volumes being exported towards the lake were significantly different. So 2015 is on the left, which was a warm year and therefore had high glacial melt, and 2016 on the right, which is a much lower meltwater year, as you can see by these kind of dashed lines here, and which is shown numerically on the right y-axis. And so the black dots here are showing the carbon dioxide flux, and any of those dots that occur above the zero line indicate when the waters along the shoreline of the lake were a net source of carbon dioxide to the atmosphere. And any points below that zero line indicate when these shoreline waters were actually a sink of net carbon dioxide to the atmosphere. And so these pictures at top really demonstrate what these shoreline waters look like. And so they're really indistinguishable from the glacial rivers, at least from a visual perspective. And so what we can see from this figure at bottom is that not only over a single season do we see that this kind of sink, or the magnitude of the sink of carbon dioxide, seems to scale with the glacial inputs, but that we're also seeing that difference happening between the 2 years. So what's interesting when we look at the lake is that the influence of these plumes is actually highly restricted to waters along the shoreline. And so these two pictures show the region where two glacial inflows actually meet the waters of Lake Hazen. And we can see that while the plumes very much affect nearshore waters, they seemingly disappear into the lake itself. And so this is the Very River at left in early July and the Gilman River in kind of mid-July within the watershed. But based on kind of the foundational laws of physics, we know that these rivers are not disappearing. So we need to peek below the lake's surface to figure out what is happening here. To look at this, we're going to contrast lake profiles from the deepest point within Lake Hazen between the open water season, when these glacial rivers are flowing into the lake, and under the 2 meters of ice in the spring, in the absence of kind of these concurrent glacial meltwater inputs. And so we still have these terrestrial inputs as a component of this budget here. And that's just because it takes a long time for some of these very finely ground sediments to within the water column itself. So here we can see these profiles. This in spring, so this is a typical lake water column profile where you have depth on the y-axis. And so these profiles are showing spring in the gray triangles and summer in the blue circles. And so in summer, these glacial inflows are so turbid that they're denser than the lake waters into which they're flowing, and consequently generate these turbidity currents, as evidenced here by these particulate carbon profiles, where we can see that the waters at the surface of the lake look very different from the depths of the lake. And so this is shown here in this picture, and this picture is actually taken in 2015, so during that high melt year. So here you have the surface waters on the left and those bottom waters on the right. And there's a big difference in turbidity, just obviously from these pictures. So these turbidity currents are capable of rapidly transporting surface waters that are saturated in oxygen, but undersaturated in carbon dioxide as a result of these weathering reactions. And these currents are transporting these surface waters to the very depths of the lake and are capable of effectively alleviating the low oxygen, high CO2 conditions that we see developing over the winter months in the absence of glacial inflows. And so the sediment core records actually suggest that this is a relatively recent phenomenon where we have this annual oxygenation of the waters at depth. What's interesting, though, is that we also see an increase in the dissolved inorganic carbon between the summer and spring months. That's largely driven by an increase in the bicarbonate ions, which we've hypothesized is the result of these chemical weathering reactions that are continuing to occur as the finer particles settle out through the water column over the winter months. So when we actually account for these chemical weathering processes, it really changes our perception of freshwater ecosystems with respect to their role in the watershed budget of carbon dioxide. So terrestrial ecosystems are obviously still dominant, and they cover the vast majority of the area across this watershed. But if we add just the glacial rivers alone, which are dominated by those chemical weathering processes, we see that this really transforms the freshwater part of this budget from being a net carbon dioxide source to a net carbon dioxide sink. So in terms of climate change, if increases in glacial melt are really predicted to occur over the near term across this region and even until 2100. And so we saw that the magnitude of that carbon dioxide sink really depended on the volume of glacial meltwater. So we might expect this sink at least to be a consistent feature of at least some glacial watersheds for a while yet to come. So glaciers are really interesting from a freshwater perspective because they not only generate rivers and lakes, but the glaciers themselves include freshwater ecosystems on their surfaces, within the ice, and underneath them. And so some work a few years ago now from John Telling at Bristol University in the UK showed that those same cycles of glacier advance and retreat that generate the finely ground sediments involved in these chemical weathering reactions are also generating hydrogen gas, which can be used in the production of methane. And there's some really interesting work coming out of Greenland from Danish and British colleagues at the moment, showing these really high emissions of methane coming from these cavities that are filled with meltwaters underneath the Greenland ice sheet. So on the left, you can see Jesper Christensen and Kristin Jørgensen at the outflow of one of these subglacial systems in Western Greenland. Where it looks like rock, but I swear it's a glacier. And so on the right are continuous measurements of methane concentration at top and flux at bottom, where we can see that these kind of emissions of methane, or this lateral flux of methane, really increases in concert with discharge from these subglacial cavities. And so we're in this kind of situation with glaciers where we're seeing these really interesting observations in some systems, but I think the next steps are really to understand how that applies more broadly across similar systems. So if we come back to those defining characteristics of Arctic freshwaters, we can see that these characteristics are already beginning to change rapidly. So we're in a situation where these are really systems that are already in flux, pardon the pun. And so we're seeing the duration of ice cover reduced. We're seeing which is increasing the potential for light and gas exchange from ecosystem surfaces. We're seeing permafrost thaw and glacial melt that are influencing freshwater quality, as well as increased productivity within terrestrial ecosystems. And all of these things together are affecting the relationship between freshwaters and their catchments, but also freshwaters in the atmosphere. And that's where we're seeing these greenhouse gas dynamics in flux. So these examples, I think, are just that. They're just a few examples of this really complex and dynamic system. But I think they highlight really this complexity around our understanding of greenhouse gas dynamics in Arctic freshwater ecosystems. And so there's so many moving parts at play. And in terms of the biogeochemistry of greenhouse gases, we're really lacking a good baseline against which to compare our current observations. But changes to these defining characteristics have really far-reaching consequences, one and not least of which is greenhouse gas dynamics. And for that, I really love this figure from the Arctic freshwater synthesis, which really centers the freshwater systems at the heart of kind of change within the Arctic. And so we can see that the effect of freshwater change in the freshwater ecosystems extends far beyond a watershed boundary. So it affects the oceans, it affects resource availability. So from a human perspective, it affects ecology and it affects the atmosphere. And so I've highlighted here just that changed evasion of carbon dioxide and methane. And so with that, I'll thank you all for your attention. I'm looking forward to the discussion with Drs. Isabelle Dorion and David Ohlefeld.
Thank you so much, Kyra. That was a really interesting talk. And it, you know, sometimes when we get really into our own research projects and programs, we kind of forget about other things we've learned maybe way back in the day. And so I just feel like I've just had a nice primer on greenhouse gases and dynamics, especially in a very sensitive and vulnerable environment like the Arctic and the high Arctic. So I think if we can, yes, we have our panelists, Isabelle Dorion and David Ohlefeld to join us. I'm just going to look at the chat box here. I don't see, there hasn't been any questions. I think your presentation was so clear and concise. So I know we'll just give some time for people to think about questions, but I think at this point I might just turn to the panel and ask, start with Dr. Dorion, if you have any comments or kind of things you'd like to kind of mention in relation to what was presented.
Thank you very much for this very, very interesting talk. I'd like maybe to start by, I'd like you to explain more about this last bit where there was an increase in methane production in these glacial lakes. I didn't understand why or how it was explained exactly.
Right. So I think they're still trying to figure out exactly what's driving, like whether it's mostly thermogenic production or bacterial production. But the subglacial freshwater ecosystems, so those are the ecosystems underneath the glacier, are really microbially active. So I think what they think is happening I was talking to Christian not long ago about this, but that they're seeing large fluxes from the subglacial system. And so we're seeing really high emissions right at the terminus of the glacier that aren't necessarily translated downstream. So they're thinking, I think it's mostly microbial production, but there's a lot of follow-up work that's happening, especially within the Western Greenland glacier systems.
Okay, okay. And so the glacial lakes, the active glacial lake, is it an important fraction of the lakes in the Arctic? Do you know?
That's actually a good question. I'm not sure if there is necessarily, I guess Dan Sugar at the University of Calgary came out with that study earlier, or in 2020, about the number of proglacial lakes. And those are some of the smaller lakes, but there wasn't necessarily as good coverage in the high Arctic. I think because some of those systems are really dynamic. And so Lake Hazen is definitely unusual because it's in the forefront of these retreating glaciers, but it's not necessarily a glacial lake in the strictest sense, because lots of those are just very small and are created kind of by the